Hello, ladies and gentlemen. Today we're going to be continuing with electric forces and fields. The topic or the focus of today, we're on section 3, which focuses on the field itself. Okay. So, an electric field, just how gravity is always present for charged particles, all charged particles have this invisible electric field around them. Okay. So let's look at this on the left side here. Let's look at this left sphere. So this left sphere is positively charged. And this positively charged sphere has an electric field around it. Okay, it has a positive electric field around it. That field is going to interact with other charges in the area. So in this case, let's say we have another smaller positively charged particle near the sphere. The electric field of the sphere is going to push away the positive particle and push it to the right. That's why you have the arrow going to the right. Okay. If you had a negative sphere, the negative sphere has a negative electric field, and that electric field is going to pull the positive particle towards it. Because remember, opposites attract. Okay. So fields act similarly to gravity. All charged particles have a field around them, and those fields can interact with each other. Okay. And remember, what's different about the electric field from gravity is that the electric field can both push and pull. Gravity can only pull, okay? It can only pull you towards it, okay? But E fields can both push and pull. Like on the left here, it's being pushed, and on the right, it's pulling. The magnitude of it can be calculated with this equation. So this is the new equation we're learning for this section, okay? It's that the magnetic field strength is equal to the electric force divided by the charge, and that actually gets rearranged a little bit, okay? That's right here, okay? So if you plug in the equation from the previous section, you get this one, okay? So if you plug in for F electric, you can cancel some things out and you get a new equation. And this is what that new equation here. So what it's saying is that the electric field of any particle is equal to the Coulomb's constant, which is just that number Kc, times whatever charge it has divided by how far you are from it. Okay, that'll tell you how strong the electric field is at that point. Okay, and notice, so what that means is the further away you get from a point charge, the less force it starts to feel. So let's go up here and look at this again. So when the particle, let's say this is my particle, the blue dot is the particle. If the particle is right next to the sphere, it feels the maximum force. But as it gets pushed away, it gets further from the field. And as you get further from the field, R increases. And as R increases, the field strength gets smaller. And that makes sense. The further away you get from the sphere, the charged particle, the less you feel the field. And that makes complete sense. Okay? That's what that equation is telling you. The field strength is related to how charged it is and how close you are to it. That's what controls that. Okay? For today, I actually want to split up this section into 2 days just because it's a little more complicated than I thought it would be to explain the way we've been doing it thus far in remote learning. I actually want to spend 2 days on this. Okay. So we just talked about the field strength. So this is the field strength. This is the equation that's related to it. Now, we eventually get to this point where they start talking about electric field lines, and that has to do with basically us trying to represent the field. So now let's talk about representing the field. So positive charges, we always, for convention, it doesn't matter which way you do it, but whatever you do, be consistent. But for here, we always say that the field is pushing away from a positive particle, okay? So positive particles, you always draw the lines going out of positive particles. So more or less the representation you see here is what you would see. If it was negative, you would have the arrows going towards the particle, okay? If it was negative, you would have the arrows going towards it. Okay, similar to here. So this is for the representation of the field lines, okay? And you may be wondering, how are we going to apply this? And we'll get to that eventually. But this is actually where I want to stop at. I don't want to make today's session long. Where are we at right now? We're at 5 minutes. But this section actually gets a little complicated. I actually want to split it up over 2 days. Okay, so we learned the new equation to find how to calculate field strength. And we learned how to represent the field itself. Okay, is there any blank spots in here? There aren't any blank spots for me to draw. Why is this relevant? Why are these lines relevant? What are they referring to? This is why it matters. So it's a way to represent kind of like the flow of electricity, how things go from one end to the other. This is what that's going towards. So when you're talking about electric fields, the lines always come out of the protons and they go towards the electrons, okay? Out of the positive into the negative. And this is what causes that attraction, but this is how we represent it, okay? Today, I don't want you to do any worksheet related stuff. What I want you to do is to play around with this simulation that I'm going to be posting with it. So there's this simulation from PHET called Charges and Fields. And what it lets you do is it lets you put different charges in different locations and look what happens to the field lines as you put them in different locations. So when you open it, I am going to request that you turn on everything. Okay, everything here, put all the check boxes on, turn on everything, and play around with it and see what happens as you interact with different things. So when I put one proton, well, let me take everything out. If you take everything out, there's nothing. If you put in one proton, you can see all the arrows are coming out of it. If you put in one electron, you see all the arrows are coming towards it. If you put more than one, now you start to see what's going on. You can see that arrows come out of the proton and into the electron, and you start to get something similar to what we were seeing here in this image. Okay, I want you to play around with it. I want you to self-explore a bit, okay, and see what's happening. You can calculate voltages. You put in the sensor, it tells you how many volts and things are in there, okay? So this is what I want you to do today. So there's no direct worksheet. I just want you to focus on playing around with this and experiment a little bit. See what you get. See what you end up getting, all right? That's it for today, ladies and gentlemen. There's no specific worksheet. Things are more complicated in this section than I intended. I have to find a way to teach it a little easier. Today, I want you to experiment a little bit and play around with that. All right? Focus on the concepts. See what's going on. All right? Enjoy the rest of your day. Take care.